Welcome to our channel. Today, we're diving deep into the world of Allen Bradley PLCs, or programmable logic controllers, and I'm thrilled to tell you that the knowledge you'll gain here will be a game changer in industrial automation. Whether you're completely new or want to sharpen your skills, this video is designed to help you level up and become more confident with PLC programming. In this video, we're taking a journey from the basics all the way to advanced techniques, exploring how PLCs have revolutionized the way industries operate. We'll be breaking down everything you need to know, from the foundational concepts to advanced programming and even troubleshooting strategies. Our goal is simple: to empower fresh engineers and control engineers across the globe. So, if you've got any questions, drop them in the comments, and I'll be happy to assist. Let's dive in and make industrial automation easier and more exciting for everyone. First, let's dive into one of the key elements of ladder logic, the output coil. The output coil is a crucial component in any PLC program. Think of it as the device that controls the action, whether it's turning on a motor, energizing a solenoid, or activating a light. In ladder logic, the output coil behaves like a switch that turns on when the input condition is true or high. It reacts to the inputs, so if the condition driving the coil is false or low, the output will remain off. Essentially, it serves as the bridge between your logical conditions and the physical actions in your system. Next, let's discuss the normally open NO contact. This symbol is incredibly common and represents a contact that starts open, meaning it doesn't allow current to flow unless the input condition is true. Once the condition becomes true, the contact closes and current is allowed to flow through. You can think of it like a gate that only opens when certain conditions are met. Perfect for controlling elements in your process that should only activate under specific circumstances. On the other hand, we have the normally closed NC contact. This works in the opposite way to the normally open contact. The normally closed contact begins in a closed state, allowing current to flow when the input condition is false. However, when the input condition becomes true, the contact opens and the current flow is interrupted. It's useful for scenarios where you want a device to remain active until a condition is met, at which point it turns off. These three elements, the output coil, the NO contact, and the NC contact, are the foundational building blocks of your PLC logic. Together, they allow you to create intricate control systems that can handle everything from simple on-off operations to complex sequences. Let's begin by understanding normally open, or no contact. Picture a light switch in your home. Most of the time, it's off by default, right? This is similar to a normally open contact. When the switch is off, no electricity flows because the circuit is open. In this state, nothing happens. No current passes through, no light turns on. Now let's shift to normally closed, or NC contact. This one works the opposite way. Imagine you're standing in front of a refrigerator. You know how the light stays off when the door is closed? That's because the circuit is closed, meaning no electricity is flowing to the light. But the moment you open the door, the circuit opens, allowing electricity to flow, and the light inside the fridge turns on. In PLCs, normally closed contacts behave in a similar way. By default, they let electricity pass through when they are inactive, but when they're activated, they stop the flow. So think of NC contacts as an automatic switch that works without you having to manually open or close it. It's like a safety mechanism, always allowing current to flow unless told otherwise. This is useful in systems where you want to ensure something remains on unless it's intentionally switched off, like emergency stop buttons or fail-safe conditions. Now, let's get started with the software for this practical training. I'll be using RSLogix 5000, along with the RSLogix Emulate for simulation, and the third application we'll be using is RSLogix Classic. We're diving into these tools because they are essential to get the software running and to enable downloading programs into the PLC. Let's begin with RSLogix 5000. I'll show you how to create a new project, select the appropriate controllers and modules, and configure everything you need. It's important to understand that selecting the right controllers and modules is crucial for ensuring your project runs smoothly. Here I am creating a new project. For this session, I'm selecting the simulator as my controller. There are multiple controller options available, but since I'm using the simulator, it allows us to test and troubleshoot the logic without needing physical hardware. In the simulator, I'll select that and name the project, for example, PLC programming. There's no protection required for this setup, so we'll move forward. Now that the project has been created, we can see the controller we selected displayed in the backplane. Next, I'll add some additional modules, like input and output modules. I'll choose digital I/O modules, but the selection depends on your specific requirements and the hardware you have available. In this case, I'll use this digital I/O modules to configure. Once selected, just click OK. These are all the options you can configure based on your needs, which will help you set up your project for success. Now I'll create another modules for digital output, but again, the selection depends on your specific requirements and the hardware you have available. In this case, I'll use this digital I/O module to configure the necessary inputs and outputs for the project. Once selected, just click OK. These are all the options you can configure based on your needs, which will help you set up your project for success. The controller has now been selected, and the input and output modules have been added. You can see in the controller properties what options are required beyond the default settings to customize the configuration to your needs. All of this is being done in RSLogix 5000, where we can fine-tune the system for optimal performance and functionality. Now, we're moving to the main routine where the actual programming happens. This is where we'll create the ladder logic that controls how the PLC interacts with the real world. The main routine is like the brain of your PLC program. It processes the input signals, executes the logic, and then sends commands to the output devices. In RSLogix 5000, we have several key programming objects to work with. First, there's the rung, which is the horizontal line where instructions are placed, similar to electrical wiring. Then we have contacts like normally open, NO, and normally closed, NC, which represent conditions that trigger actions. Coils represent outputs, like turning on a motor or light. There are also timers and counters for creating delays or counting events. These programming elements will allow you to build complex logic, automate tasks, and control machinery efficiently. Now let's start by adding a normally open NO contact and a coil to our ladder logic. The NO contact represents a condition that allows current to flow when it's energized or true. When the input condition is met, the contact will close and the logic will continue down the rung. Next, we need to assign an address to both the NO contact and the coil. The address for the NO contact links it to a specific input or tag in the PLC, like a button or sensor, allowing the PLC to monitor that input. Similarly, the coil must be addressed to the appropriate output, which could be linked to any device you want to control. Proper addressing ensures that the PLC knows which input to monitor and which output to activate. Now let's talk about controller tags. In RSLogix 5000, Tags are used to identify and store data for inputs, outputs, and internal variables in your program. Controller tags are global, meaning they can be accessed from anywhere within the project. Each tag has a unique name and can be assigned to physical I/O points, memory locations, or program elements like timers and counters. By creating and managing these tags effectively, you ensure that your PLC program can monitor and control the necessary devices and signals. Let's assign addresses to our No Contact and Output coil. For the NO contact, I'm selecting the 0 bit of the input module. This means we're using the first input point for the contact. Once you've assigned these addresses, you can also add comments by using the Edit tag option, which helps label and organize your code for better understanding and troubleshooting later on. Similarly, for the output coil, I'll assign the 0 bit of the output module. This will activate the first output when the logic condition is met. With these addresses set, the PLC knows where to get the input and send the output. Once you've assigned these addresses, you can also add comments by using the Edit tag option, which helps label and organize your code for better understanding and troubleshooting later on. Now, verify and compile our program to check for errors. I'll click on the Verify button to identify any issues, and once resolved, we'll compile the program to ensure it's ready for downloading to the PLC. This step is crucial for confirming that our code is error-free. Now, I'm starting the RSLogix 5000 emulator and RSLogix Classic to set up for real-time simulation. The emulator allows us to test our PLC program without needing actual hardware, giving us the flexibility to see how our logic behaves in a controlled environment. It's taking a moment to open, so let's wait patiently. This process can take a little time, but once it's ready, we'll be able to continue with our training and see our program in action. And yes, it opened. I'm currently removing all the modules to set a new configuration. This will allow us to customize our setup according to our specific project requirements. It's important to start fresh to ensure everything is correctly configured for optimal performance. Let's proceed with this adjustment. I'm now adding the controller in the slots as defined in the project. This includes configuring the digital input, DI, and digital output, DO modules. Ensuring that these modules are correctly placed is crucial for proper communication and functionality in our PLC setup. Let's make sure everything is aligned correctly. RSLogix Classic serves as the communication link between our programming software and the emulator, enabling us to monitor inputs and outputs in real time. Let's get everything up and running so we can see our program in action. Let's make sure the RSLogix Classic drivers are properly configured, just as shown here. This step is essential for establishing a reliable connection between our programming software and the PLC. By verifying the driver settings, we can ensure that our system communicates effectively, allowing for smooth operation and monitoring of our project. After setting up the emulator 5000 and configuring RSLogix Classic, we are now ready to perform the download. This will transfer our program from RSLogix 5000 to the emulator, allowing us to run and test the logic in real time. Let's proceed with downloading the project and see it in action. I've now selected the controller, and we're ready to perform the download. This will transfer our configured program to the PLC or emulator, allowing us to test and monitor the system. Let's initiate the download and move forward with the simulation. Unfortunately, we've run into an error while trying to go online with the controller. This can be really frustrating, but it's a common issue. It often happens when the controller and I/O cards aren't placed correctly in their predefined slots on the backplane. Let's double-check the configuration to get things back on track. The error occurred because in the simulator, the controller is placed in slot 2, the digital input DI module in slot 3, and the digital output DO module in slot 4. However, in the program, the controller is configured in slot 0, the DI in slot 1, and the DO in slot 2. This mismatch between the actual slots and the program settings is the reason for the error. I'm now updating the Project I/O card settings to match the configuration in the simulator. This means setting the controller to slot 2, the digital input DI module to slot 3, and the digital output DO module to slot 4. Once the settings are aligned, we should be able to go online without errors. I'm saving the program again with the updated I/O card settings. I'll verify it to ensure there are no errors in the configuration. Once the verification is successful, we'll go ahead and perform the download to transfer the program to the controller for real-time simulation. Before proceeding with the download, make sure you've carefully read and understood all the instructions. Ensuring that everything is properly configured will help avoid errors during the download process. After a successful download, you'll be able to go online with the controller and monitor the real-time status. This will allow you to see how your program is functioning and interact with the system directly. I'm now enabling forcing to manually control and observe the input and output statuses. This feature allows us to simulate real-world conditions and verify that the logic is working as expected, even without physical inputs. As I force the normally open input, the output goes high, indicating that the condition is true. Conversely, when I disable the force on the input, the output will return to low, showing that the condition is now false. This demonstrates how the logic responds to input changes in real time. Now, I'm adding a normally closed NC contact using the same input address in another rung as the normally open NO contact. This setup will help illustrate the difference between the two types of contacts. While the NO contact allows current to flow when the input is true, the NC contact will block current flow under the same condition. Let's see how this affects the output during our testing. Both outputs are assigned different addresses to effectively test their behaviors. This setup will allow us to observe how each contact NO and NC affects its corresponding output under the same input condition. Let's see how these distinct addresses impact the output responses during our testing. After adding new rung, save the program once more and verify it for any errors. It's essential to ensure everything is correct before proceeding. Once verification is complete and no errors are found, we can download the updated program to the controller. After the download, I'm enabling the forcing again to perform a test. This will allow us to observe the differences in behavior between the normally open NO and normally closed NC outputs. By forcing the input, we can clearly see how each output responds and deepen our understanding of their functionality. We can see that the output with the normally open contact gets energized when the input is forced. In contrast, the output with the normally closed contact is de-energized under the same condition. This clearly demonstrates the fundamental difference between NO and NC contacts in our PLC programming. Similarly, we can add a timer to execute the output after a specified delay. This allows us to control when the output is activated based on the timing conditions we set. I'll simply add the timer here, and we'll dive deeper into how to use timers in our programming in the next video. I'll guide you through the process of tagging the TON timer in detail. We'll explore how to properly configure it and utilize it in our PLC programs, ensuring you have a solid understanding of its functionality and applications. Stay tuned.